All right, so second part of this talk, I want to go on and we want to interpret the principal symbol of an elliptic operator as a K-theory element. So I sort of recalled what the K-theory of a compact space X is and the relative K-theory. Now I want to talk about K-theory with compact support. This stands for K-theory with compact support. So we define that in a very similar flavor as that one here. We want to basically say, oh, we have triples consisting of two vector bundles, E plus and E minus, over that space X, and a vector bundle map between them. But instead of specifying where that thing is an isomorphism, we want to say, hey, it should be an isomorphism outside of some compact set. Alpha is an isomorphism outside some compact set. Subset of X. And then you sort of do similar equivalence relations as up there. So you're saying, well, you know, yeah, there's obvious notion of isomorphism of these things, an obvious notion of sort of adding identity map of another vector bundle, and an obvious notion of homotopies of these alphas. Of course, keeping the restriction that while you're deforming, you still should have an isomorphism outside a compact set at all times. But it doesn't need to be the same set as you deform your vector bundle map. Okay, so
is that modifying that equivalence relation? Is that the same thing as taking the co-limit of the k of x comma x mod c?
Yes, I believe that this compact supported K-theory is equivalent, can equivalent be defined by taking a co-limit over compact subsets of X. Okay, so this is a very convenient way to think of this K group, right? Since now, if we have D, an elliptic operator, then we have our principal symbol, right? The principal symbol of this operator D is a map from the pullback of the domain vector bundle in the pullback of the range vector bundle. So this is the principal symbol. Of D. And then you see this is invertible outside the zero section of the cotangent bundle of X. So does that have compact support? Well, if X is compact, then it has compact support. So this one here, in other words, is an element in compact supported K-theory of the total space of the cotangent bundle if X is compact. It will be convenient to think slightly more general. Well, what happens as X is not compact? It's still true that the this vector bundle map will be an isomorphism away from the zero section. But the zero section, I mean, that's homomorphic to X, so that's not compact then. But we still have something which I will call vertically compact. Since if you intersect this given thing with the pre-image of a compact subset of X, then you will have, again, something which has compact support. So I will call this vertically compact. In general. So this is vertically compact. So this is compact in the vertical, i.e. the fiber directions. Okay. All right, so we have, for compact manifolds in particular, we have a nice interpretation of this symbol as an element in the K-theory of the cotangent model with compact support. And here's a cool fact, namely, the index of this elliptic operator will only depend on that K-theory class. Index of D depends only on the class of that the principal symbol of D represents in the K-theory with compact support of the cotangent bundle. And this is, of course, a statement for X compact, since otherwise the index doesn't make sense. So for compact X, depends only on that. So that brings us a step closer to saying, oh, then there should be a topological description of it, right? So then the obvious question is there a topologically defined map, homomorphism, which will be called the topological index from that K-theory group with compact support of the cotangent bundle of X into Z. And then the hope would be, well, if there's a canonical thing that we can construct using topological means, then we should hopefully prove at the end of the day that it agrees with the index. So that's sort of the goal. So that's the next thing we want to talk about.
Is there some way to think about this K-theory class as being fetched from something attached to the edges on X?
Well, the symbol, the principal symbol, is defined patchwise if you want to, and
on the language of sort of K-theory class itself, you could assemble it on the length and on the K language.
sort of like, I mean, vector bundles can be described by sort of their transition functions in the same way K-theory classes can be defined in terms of transition functions. So if you prefer that, you could use an atlas and then produce sort of transition functions for any double overlaps.
Is there any... Maybe I'm anticipating something you're going to say. Maybe this is a bad question, but I'll say it anyway.
Anticipating questions are good.
I mean, couldn't I also think about this symbol as being a class in the relative cohomology group T star, or the K cohomology T star X, comma T star X minus the zero section?
Absolutely. Yep.
Okay.
Yep. Maybe I should write this down. So equivalently, this can be sort of as the K theory of that, comma, zero section.
I'm inclined to think about this as, wait, no, not that. T star x minus.
Sorry. Yeah, absolutely.
My motivation for saying this is where I always think complex resides.
Okay, sounds good. Yeah, and I think in terms of compact support, so
Okay.
whatever is more convenient. But yeah, it's good to have both points of view down. Yes, minus the zero section. Since on this region, your principal symbol is invertible, so yeah, therefore you can view it as a relative K-theory class living in that relative everything away from the zero section. Okay, so the third part of my talk is about the construction of this top index map. So this will be a homomorphism, as I wrote down there, from K-theory. And let me write down compact support again.
So is there an equality?
Into Z. Is there what?
I see like a vertical equal sign that I'm confused about.
There's a vertical equal sign, yes. So this is an alternative way to think about the K-theory with compact.
Maybe the vertical?
Oh, vertically compact support, yes. Well, I guess here I'm sort of thinking about compact X anyway, and if X is compact, then it doesn't make a difference, right? But, so X is compact. But the general statement is true that this way of thinking corresponds to the vertically compact thing. So maybe I should write this down more generally. For any X, compact or not, we can identify the vertically compact version of the cotangent bundle with the K-theory of the total space relative the complement of the zero section. Yep, pretty good. Okay. But for non-compact X, we of course don't expect to have this map to Z, right? So how do we construct this? Well, the main tool will be a topologist tool, which is a so-called Thoma isomorphism. So assume that, say, V is a vector bundle, a real vector bundle, of, say, dimension K. Then I want to look at, I would like to sort of phrase this in a very general discussion. So let's think about a general cohomology theory, which can be K-theory, can be ordinary cohomology, or one other more general cohomology theory. So let's see, E, it's a generalized cohomology theory. So the main thing I'll be thinking of, that could be K-theory, ordinary cohomology. And the thing I want about this, it should be multiplicative in the sense that it should have cup products. So with cup products. So in other words, I can take a an L-dimensional cohomology class and a K-dimensional cohomology class. I can take the cup product to get a K plus L-dimensional cohomology class. Okay, then let me look at what the cohomology class of a fiber here of this bundle is. So I pick a point X, and I write Vx for the fiber of this bundle at the point X. And let's look at the cohomology applied to Vx, but I want to take with compact support. And then there are various ways to think about it. One way is to say, oh, that's the same thing as what you said. So you take the vector space Vx relative to Vx without 0. Or another way to think about it, the compactly supported cohomology is the same thing as the cohomology with, of the one-point compactification. So let me write V plus for the 1-point Vx plus for the 1-point compactification. And, well, the 1-point compactification of a k-dimensional vector space will be a k-sphere, right? So you're really talking about, oh, and reduced, yes. And that, of course, is just a sphere, so this is isomorphic to the reduced cohomology of a k-sphere. But then I can have, again, suspension isomorphism. That will say this one here is really isomorphic to the K theory, K dimensions lower, to the unreduced E theory of a point, K dimensions lower. Okay? So I have this sort of chain of morphisms. This is a chain isomorphisms of what kind of things are these? Well, all of these things, I can use my cup product to say they are all modules over the cohomology, the E cohomology of a point. Right? So these are all isomorphisms of modules over the E cohomology of a point. Right? Can multiply with that. So what is it saying? Well, this thing here, well, that's obviously free as a module over the E cohomology of a point. It's a free module. So that is saying that, oh, this one here is a free mod is also a free module. What's that? Oh, yeah, this is a reduced theory. So the this is defined to be the kernel of the map from E tilde of E of whatever space we're looking at under the restriction map to just E of a point. And that works for any space X. So maybe I have a general point space X here, then the reduced E theory of X is always defined as a kernel of that. So the upshot of this is that this thing here is a free module over the E cohomology of a point. All right. So that will motivate now the notion of an E orientation for a vector bundle, this vector bundle V here. definition, an E orientation, also known as Tom class, for this vector bundle V over X is an element tau in the E-cohomology of vertically with compact vertical support of this total space, which is the same thing as what Mark likes, maybe the E-cohomology of space V relative to V minus the zero section. Such that if I restrict this element to the fiber over any point x, this one here is then an element in the E-cohomology of this compact support of the fiber. And this should be a generator of this V module. Okay. So, for example, for ordinary cohomology, picking a cohomology class with compact support in the total space with a property that each restriction to a fiber is a generator is the same information as an orientation on this vector bundle. That's sort of where this name comes from. That's the historical origin, but you can do it with a very general cohomology theory, and we'll be in particular interested in K-theory. Okay. So what is the use of this sort of E-orientation? That's an important theorem. So suppose tau is, let's say it lives in E n.
So we concluded that we had a free module, but we didn't conclude that it was dimension 1. Is this
Oh, no, a free module of dimension 1. Sorry, I meant to write this of rank 1. Yes. Yeah. And that's why I want just one generator. Yes. Thank you. Now, suppose that we have an element in this thing with vertical compact support of V, that this one is an orientation, then I have a map from the E-cohomology with compact support of the base space X into the cohomology with vertically compact support of the total space of V, which works by multiplying by the Tom class. So if I have any class alpha here, then I take tau and I multiply it by alpha. So this is the cup product. In the case of K-theory, which we were interested in, this will be given by a tensor product of the bundles and vector bundle maps involved. It's a tensor product. If the cohomology theory is the K-theory. And it's the ordinary cup product if the cohomology theory is the ordinary cohomology. and is given by, if you think in terms of de Rham cohomology, it would be the wedge product of these forms. Okay, so wedge product if the cohomology question is the de Rham cohomology. Oh, yeah, right. So I need to, exactly, thank you. So the alpha is a class in X, and then I have the projection map from the total space of my bundle pi into the base space, and then I pull back alpha. Now notice the following thing. So we need to check that this one here, sorry, and I meant to write compact support, not vertically compact support. I meant to write compact support here. So why should this have compact support? Well, if you think about the total space here, this way, these are the sort of fibers. Here's my projection map down to X. So the class alpha has maybe support in this set here. This is the support of alpha. So then what is the support of the pullback of alpha? Well, it will be anything, colored chalk? No, colored chalk. So then the pre-image here, this is where the support of pi star alpha lives. Oh, thanks very much. And then you see, oh, if you now tensor it with this is the support of pi star alpha. Now, what is the support of this tau? Well, it has vertically compact support. So it's supported almost very close to sort of the zero section. Only on the zero section it goes sort of wrong, right? And so, yeah, this has not compact support, but if you intersect it if you take the product with pi star alpha, then the support intersects, and so the support will be just the part of the green thing which is inside the red region. That's why you end up with compact support here. Okay, and the statement is, this Tom isomorphism theorem says that this map here is an isomorphism. Now we want to put that to good use.
Very brief comment. It's also true if you don't have the, if you put VC on one side and no C on the other side.
That's right, yes. You can play with these compactness conditions.
Extremely minor thing to say, star plus K.
Oh, yes, 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 absolutely. No, I definitely wanted that in there. Thank you.
So in the definition of an E-top class, do you require that tau to be in degree K?
Yes. Yes. Yeah, let me just write K here.
The Tom class is equivalent in many different dimensions. You know, like in K theory, typically the Tom class moves in K equals 0. Whereas if you're dealing with regular cohomology, the Tom class typically lives in the degree of the real degree of the vector.
Right. Does that? Now I want to use that to construct a map in the following situation. Now suppose that X into Y is a proper embedding of manifolds. say, with normal bundle n. N is a normal bundle over X. So then you can, let's call this embedding F. Then you could sort of pull the following thing. You can say, okay, well, let's start with an element. Let's start with a group, the E-cohomology with compact supports of manifold X. Let me sort of maybe assign dimensions here. So let's say this N is a k-dimensional bundle. So in other words, it's an embedding of codimension k. So then I can do the following thing. I can take an element in the E-cohomology of X with compact support, and then I can use my Tom isomorphism. Multiply by my Tom class to say, oh, that's isomorphic to the cohomology with compact support plus k of the total space of my normal bundle, right? Now, I claim there's a map of this into here, since, well, you can identify, let me just do it like this. So you have the original embedding of X into Y. Now, the tubular neighborhood of X inside Y can be identified with the total space of the normal bundle, right? That's the tubular neighborhood theorem. And so that is saying that X sitting inside N as its zero section, that can be extended to an embedding of this bigger thing. So this one here, the image is a tubular neighborhood of X inside Y. Neighborhood of X in Y, or f of X in Y. Should I draw a picture of that, or is that pretty clear for everybody? Okay. Well, so I can think of N as being sitting as a codimension 0 submanifold of Y. And this is, again, going to be a proper embedding here. So it's a proper.
So the arrow between homologies goes that way because it's compact support.
Exactly. So that's exactly the point. So I have a cohomology class in here, which is supported on some compact set thing in here. Well, under this proper embedding, that goes to some compact thing in there. And then I can say, oh, OK, just sort of then look at this class that you have here, which is supported on that compact subset. Look at it as a class here supported in that same compact subset. So you could sort of think of this map here as extend by 0, right? Say, think of differential forms. If you have differential forms that sort of are supported in a compact set, that means they're just identically 0 outside, and then you just extend by 0 outside that. So you have a map going that way. Oh, OK. So you have a map now. Let me denote this map, and let's call it F shriek. And so notice that it sort of, it's a funny map, right? It goes sort of the wrong direction for cohomology. It goes in the same direction as the original map F. That's why I put the shriek as a subscript to indicate that. And it makes a funny shift of degrees given by the codimension. OK, it was it is. And that, of course, uses the fact, so F shriek can be constructed constructed. So what did we use for this one here? The crucial thing was that we had the Thom isomorphism, right? So can be constructed provided the normal bundle N comes equipped with an E orientation. That's a crucial ingredient here, right? Since this map is given by cut product with that orientation class, and if we have the orientation class, yes, we can form this composition here. It's a crucial ingredient. So now I want to apply that. And in the application, my manifolds will be the following. So now I have smooth manifolds, embedding here, smooth manifolds, proper smooth embedding. Embedding of, say, codimension K again. It's normal bundle N. Bundle N. I don't want to apply it to this one, though. I want to rather go to the tangent space. And the differential of the original map induces a map in here, which again is going to be a smooth, proper embedding. With normal bundle, so what's a normal bundle here? Well, then you have sort of the normal bundle sort of in the base direction, right? That was N itself. But on each fiber, you see also the normal bundle in the fiber direction. So you have basically the sum of two copies of the normal bundle as the normal bundle of this sort of new embedding here. So the normal bundle is N plus N. But of course, N plus N would be a bundle over X, and I need to pull it back to the total space of the tangent bundle, pi star, where the pi is the projection map from the total space of my tangent bundle of X to X. So I get this normal bundle here. Now notice that this normal bundle here, I can think of as a complexification of N, right? Sum of two vector space you can always identify with the complexification of that vector space. So in particular, that means the normal bundle of this embedding now is a complex vector bundle. So this is a whole thing now becomes a complex vector bundle. Why is that helpful? Well, the helpful fact is that there is a K-theory orientation for complex vector bundles. It's often called the Atiyah orientation of complex vector bundles. Complex vector bundles have K orientation. In other words, the complex structure on that vector bundle gives you a built-in K orientation. And not today, but maybe at some future point, I will talk about the construction, how to write down this K orientation of complex vector bundles. Okay, so that means, hey, we can make this construction if our homology theory is K theory and the embedding we apply to is really the differential of the original embedding, right? Hence, get map. So I get a map. So we have originally the K-theory with compact support of our cotangent bundle of our manifold X. Now the thing that I'm going to always do is notice that the tangent bundle and the cotangent bundle are isomorphic as bundles. Say choose a Riemannian metric, and that provides such an isomorphism. So this is via, say, a metric on the manifold X. So I'm always going to just sort of from now on work with the K-theory with compact support of the tangent bundle. And then I have this map that's associated to this proper embedding, the Schweik map, that will go from the K-theory, compact support of X in the K-theory of compact support of Y. So you might say, oh, wait a minute. Isn't there sort of the dimension shift there? Isn't there a shift here? So if I start with K0, which is a K-theory as we defined it, I end up with 0 plus 2K, since that is the new codimension, right? Since the original codimension is K, then this will have codimension 2K. So I have a shift here. But then the K-theory is too periodic. Complex K-theory is. So no, I'm always going to identify that again with just the K-theory of that. So that's why I don't have a dimension shift. Okay, so I have this map here. So now how I'm going to, this is the main ingredient in the topological index map. So now comes the definition of the topological index map. So to define topological index map, pick an embedding of your manifold X into, now we specialize our manifold Y to be just a huge sphere. Embedding. And so this should be embedding. Embedding. And I'm assuming now that X is compact. So it's automatically a proper embedding. So that's my embedding F here. I also have the embedding J of a point into Sn. So then I'm going to go like this. So I want my topological index map to go from the K-theory of the tangent bundle of X into the K-theory of a point, right? How is that going to work? Well, the first thing I do is I look at the induced proper embedding of the differential of F. The associated Schweik map then brings me to the K-theory with compact support of the tangent bundle of Sn, right? And then I have, then I apply this to the embedding of a point into Sn, right? That's also a manifold, so I apply my Schweik map in that case. I take tangent of J and take the Schweik of that. That gives me a map from the compact, from the K-theory of a point, from the tangent space of a point. It's all a little bit of an overkill here, but that's tangent space of a point is a point again, right? Now, this one here, this group is Z, K-theory of a point. This map here, if you think about it, hey, this is just an isomorphism. Since, yeah, think about it, and this is an isomorphism. It's just a... So that is what we want, right? We have now constructed by topological means a map from this group into this group. That's defined to be the top index topological index map. So now the index theorem is sort of the statement, hey, those two things agree. Index theorem. And that's due to T and Singer. And there are many, many different ways to formulate the index theorem. It can either be formulated as a theorem for a general elliptic operator, the way we do here. It can be phrased or for concrete operators like the Dirac operator and Dolbeau operator, etc., pp. Or it can be phrased in terms of K-theory, like we did here. Or it can be phrased in terms of cohomology. So there are lots of different versions. So this is, to me, the version that is maybe most encompassing for the time being, but also probably hardest to work with, since this topological index map is a little mysterious, right? That becomes a lot more hands-on, and for calculations, you want to say that in cohomological terms rather than K-theory terms. But that's a translation. So this version of the index theorem is the K-theory version, as opposed to the cohomology version. And it just says that if D is an elliptic differential operator on a compact manifold X, then the index of D is actually can be calculated in this topological way. Namely, you start off with the principal symbol of D. This represents an element in the K-theory with compact support of your tangent or cotangent bundle of X. And then you can use these maps here, namely the top index map, defined over there, to get an element of the K-theory of a point, which is C. So that's the statement. So the left-hand side is sort of the analytic side, where you talk about the index of an elliptic operator, and the right-hand side, that's pure topology, and you're talking about K-theory classes, and you push them around, right? Okay. So in the last few minutes, let me sort of outline how the proof is sort of working. So this is a very, very, very rough outline. Outline proof. So the right-hand side has a nice formulation in terms of this topological index map, which is just a homomorphism from a K-theory group into the K-theory of a point. Now, it would be nice to also have such a formulation for the left-hand side. And there is such a thing. You define an analytic index map, homomorphism, which has the same domain and range as the topological index map, namely the K-theory with compact support of the cotangent bundle of X, and the range is K-theory of a point, which of course is Z. But this map is defined in a very different way. It starts with any class sigma in here, any class U maybe. And then what you do is you say, oh, we know that the index of an elliptic operator does only depend on its principal symbol. So let's try to construct an elliptic differential operator which has U as its principal symbol, and then take its index, right? So you take the index of D, where D is any elliptic differential operator with the principal symbol of D equal to the given U in the K-theory of the cotangent bundle. And so the only question is, well, can you, for every element in this K-theory, can construct such an operator? And yeah, that sort of means to do that. So then it's really boiling down to saying, well, you have these two different, totally differently defined homomorphisms, and you want to show that they are the same. So I need to show that the analytic index map is equal to the topological index map. So to do that, you study certain properties of this analytic index map. And that's really where all the hard work is. Here two properties. The first one is really simple. The second one is a real tough one to show. So the first one is, well, what happens if you do it for a point, right? So if you look at the analytic, so if x is equal to a point, then the analytic index map is a map from the K-theory of compact support of the tangent bundle of a point, right? Well, that's still a K-theory of a point into K-theory of a point. You want to say, oh, that's the identity map, right? So that's not hard to show, since we totally understand elliptic operators on the one point. Okay. The second property is really a tough one. So let me look at the analytic index map. So that's a map from the tangent bundle of your manifold X into K-theory of a point. That's analytic index. And let me indicate which manifold we're on. So this is the analytic index map for the manifold X. Now, suppose that I have an embedding of X into Y. So proper embedding. Yeah, this is, it's an embedding. It's always automatically proper, since I'm assuming that the manifolds we're talking about are compact, right? Only for compact manifolds does the definition of the analytic index map make sense. So then I have the analytic index map for the manifold Y as well, for this bigger manifold Y. But these things are related via this embedding here, right? Since we said in this construction up there, whenever we have an embedding of these compact manifolds, we get a proper embedding of the tangent spaces, and that induces this map that we call TF Schweik. So here's the map TF Schweik. This one here, the statement is that this diagram is commutative. Okay. All right, so this is the hard part. This is easy to show, and this is hard analytical work to show this. But once you have that, you're home free. So the rest is totally formal. Okay, so let me now look at the analytical index of an element U. Right. So by definition, this is analytical index from the sorry, what am I saying? So the first thing I'm going to use is I'm going to use the second property here to embed X into some huge sphere by embedding F. Right, then by the second property here, I have this commutative diagram here. So this is the same thing as the analytic index for the sphere of the class that I get by transporting the class over via this map here, right? Now, let me again use this embedding of a point into Sn, call this J. And then I have the corresponding Tj perp. That's a map from K-theory of a point into K-theory with compact support of the tangent space of the large N sphere. And the point here was that is an isomorphism. So I can rewrite this one here in a totally artificial way as T of, I apply Tj shriek inverse to this element, and then I apply Tj shriek again. Right? That way, that's the identity, so that doesn't do anything. So this is obviously the same as this one here, right? Everybody happy so far? Okay, now I use part 2 again. So by property 2, but now applied to J. This is saying, oh, the analytical index of Sn applied to this Tj, that's the same thing as the analytical index of a point applied to that stuff here. Tj shriek inverse times Tf. Right? Just formal. But the analytic index for a point, oh, this is supposed to be the identity by part 1, right? By property 1. So this doesn't do anything. So this is just that. This is just Tj shriek inverse times Tf shriek applied to U, right? But that was our definition of the topological index applied to U. So by definition. Okay, so that proves the Atiyah-Singer index theorem, if you know this hard property there. Let me just sort of make a comment here. The next sort of topics that would be natural to explore would be to say, oh, it's kind of interesting. So as far as index theory goes, it's really about the K-theory of that with compact support of the total space there. So now you could ask, oh, so don't we have the Tom isomorphism for this thing here? So that this is really isomorphic to the K-theory of X, right? The answer is, well, yeah, but you need the orientability, right? So the question is, for which X is the tangent bundle K-orientable? And it turns out that, well, if X is a spin manifold, that gives you an K-theory orientation. Actually, you need slightly less. You just need a spin C structure, but it's easier to think of spin structures for me. So a spin structure will do the job. Oh, and then you have an interesting question. So, okay, assume that X is a spin manifold then, so that you have this Tom class, this K-theory orientation. Then you could ask, well, so then you have this sort of very specific, very sort of primordial class there, namely the K orientation of that, right? What operator does it correspond to? Like this E orientation is sort of the mother of all K-theory classes in the sense you get any other K-theory class of the total space with compact support by just multiplying by an element in the K-theory of the base space. So in that sense, the K orientation is sort of the mother of all K-theory classes of that total space. So then you could ask, okay, what is the mother of all operators, right? Meaning an operator, what is the operator whose principal symbol is exactly that Tom class? And the answer is, that's the Dirac operator. Okay, well, how do you get all the other symbols? Well, you get all the other elements in the K-theory of Tx by taking your Tom class and multiplying with something that you pull back from your manifold. Okay, the principal symbol of what operator is that? Well, it's the principal symbol of the Dirac operator twisted by a vector bundle on your manifold X. So in that sense, if you have a spin manifold, it's very natural to think of these differential operators just to dispense of most of the differential operators and just talk about Dirac operators twisted by vector bundles. These are all very special from an analytic point of view since they're all first order elliptic differential operators. But for index theory purposes, I mean, they generate the whole K-theory of that. So from index theory purposes, there's no reason to look at all these sort of other elliptic operators. And so a natural extension would be to say, okay, well, let's construct the Dirac operator and the twisted Dirac operator. And then the other part is, well, okay, how do you calculate the index of twisted Dirac operators in more explicit cohomological terms? So these are the other parts that I hope to do maybe at the beginning of the fall semester. Thank you. Any questions? Go ahead.
The definition of the topological index reminds me of the point dragon time construction. If you replaced KC with Bordism, and it looks like you get the Bordism class of you get a map from the Bordism theory of a manifold into the Bordism theory of a point.
Mm-hmm. Yes. No, your reaction is exactly correct. If you write down this, what I call the extension by zero map for K-theory classes with compact support, if you write this down in terms of sort of Tom spaces, what you see is a collapse map that collapses, say, everything outside of a tubular neighborhood to a point. And you can describe these things in that term. But this collapse map is also the main ingredient in the Pontryagin Tom construction. And so yeah, these things are intimately related.
And like, think about embedding this TJ streak. That sort of reminds me of the alternate description of Pontryagin time construction in the case of frame Bordism, which is you take the inverse image of a regular value of the embedding of the map from your manifold into Sn. It's like if you're doing manifold to framing, then that gives you a map. That gives you a map. Sorry. Oh.
That's okay. All right, any other questions?
So,
Go ahead.
If we think about our very basic analytic example of the Laplacian, so the topological part becomes trivial, right? Because so the symbol is the identity, so the K theory class is 0.
Yes, yes.
Okay.
Or another way to see that, hey, the Laplacian is self-adjoint, right? So the dimension of the co-kernel is equal to the dimension of the kernel.
that's-
So,
yeah.
yeah. Mhm.
Just historically, was this sort of understood in special cases, and Atiyah and Singer sort of had the insight about how to make it general through this Thomite sort of? I mean, what was the rough chronology?
There are definitely precursors to the Atiyah-Singer theorem. So, for example, there's the signature theorem by Hirzebro, which expresses the signature of a manifold, which is a topological invariant, in terms of characteristic numbers, which are different topological invariants. But then if you use Hodge theory, you can identify the signature with the index of a differential operator. And then you can say, oh, so he proved the index theorem for this very particular differential operator. And then there's sort of, I think historically also before this came the Dolbeault operator. So you roll up the Dolbeault complex into one operator, and you ask, well, how do you calculate that index? And that index turns out to be the Todd genus of this manifold. And I think that is another case that was done first before this most general thing was done. But I think the Todd genus probably was also done. The Todd genus was defined by Hirzebro, but I don't know that he had the theorem saying that that's equal to the index of the Dolbeault operator. And so
it wasn't defined by Todd.
Good question. The name strongly suggests it just belies my heritage, I guess, coming as a student of Hirzebro. I think, oh yeah, that was Hirzebro with his multiplicative genera, right?
There was also something called the Rothman's theorem, which could have been. I don't remember what was the chronology there.
Yeah, that was definitely before, and it is a pre-theorem which says, well, the signature of a four-manifold, which is spin, is divisible by 16, and now it can be viewed as a falling out immediately from observing that the Dirac operator has a quadratic structure in dimension 4, and hence its index must be even. And so there's a lot of precursors. But Atiyah and Singer were the first ones to construct this Dirac operator on a general spin manifold. And that was sort of the key to then sort of get everything. And all right, thank you.
Thank you.